All right, today we're going to tackle a problem that pops up all the time in tech interviews, merging linked lists. This is one of those fundamental skills that, if you can master it, will have you walking into your next coding challenge with a whole lot more confidence. You know that feeling, right? We've all been there. You see the problem, you think, okay, linked lists, I've got this. But then, when it comes to actually connecting the nodes and managing all the pointers, things just trip you up. Well, today we are going to completely demystify one of the most common versions of this problem.
Okay, let's dive right in. So what are we really doing here? At its core, merging linked lists is like taking two separate, already sorted lines of people and weaving them together into one single, new, perfectly ordered line. It's all about looking at the front of each line, picking the smaller value, and linking them up to build out that final chain.
So here's our game plan for today. We're going to start with the basic challenge itself. Then, we'll master the iterative solution. That's the big one. After that, we'll look at a different way of thinking with recursion, tackle some tougher scenarios you might see in an interview, and finally, we'll see how this all connects to the bigger picture with merge sort.
So, what exactly is the problem we're solving? Because, when an interviewer says merge linked lists, they're almost always testing you on a very specific and really crucial assumption about the list you're starting with. And that one little word is sorted. The vast majority of the time, the problem assumes you're starting with two lists that are already in ascending order. This single assumption is the absolute key that unlocks the most efficient solutions to the problem. All right, let's get into the main event, the iterative solution. This is the bread and butter approach that you absolutely positively have to know. It's efficient, it's pretty clear once you see it, and honestly, it's what most interviewers are going to be looking for first. The logic here is actually pretty intuitive, a lot like how you'd merge two sorted arrays. You just look at the head of both lists, you pick the one with the smaller value, you attach it to your new list, and then you advance the pointer of the list you just picked from. You just keep repeating that simple compare and attach process over and over. But this brings up a really common stumbling block. That loop works great once you have a result list to attach nodes to, but how do you get it started? Handling that very first node can lead to some clunky if statements or some other special case logic that just isn't very clean. And the elegant answer is what's called the dummy node trick. This is a classic pattern in linked list problems, and it is so useful. Basically, you create a temporary placeholder node that just acts as a fake head for your new list. So here's why that's so great. The dummy node gives your tail pointers something to point to right from the beginning. This means you can start your main loop immediately without writing a separate block of code just to handle that first element. It completely gets rid of that annoying edge case.
And the performance on this thing? It's fantastic. The time complexity is O of n plus m, which makes perfect sense, right? We have to visit every single node in both lists exactly one time. But the real star of the show here is the space complexity, O of 1. That means we use constant extra space. We're just rearranging the existing nodes, not creating a whole new copy, which is incredibly efficient.
Okay, quick gut check for you. If we're using this dummy node to start our list, why does our function return dummy.next at the very end, instead of just dummy? It's because the dummy node itself is just a placeholder. It's not actually part of our data. The real head of our newly merged list is the very next node we attach to it. Now, let's explore a different way of thinking about this. While the iterative solution is king for its space efficiency, recursion offers a really elegant and sometimes conceptually cleaner way to look at the same problem.
And right here, this slide highlights a classic trade-off in computer science. The recursive code can be beautifully short and clean. It basically boils the logic down to the final merged list is the smaller of the two heads attached to the result of merging the rest. But, and this is a big but, that elegance comes at a cost. Every time that function calls itself, it adds a layer to the system's memory on the call stack. So our space complexity balloons from O of 1 to O of n plus m.
So, you've mastered the standard problem. Now let's crank up the difficulty and look at the variations an interviewer might throw at you to really see if you know your stuff.
What if the lists aren't sorted? Well, if the final order doesn't matter, it's super simple. Just run to the end of the first list and tack on the second. But if you need a sorted output, the best approach is usually to just combine them first, then run a sorting algorithm, like merge sort, on that big new list.
Now here's a true classic advanced problem. Merging k-sorted lists, not just two. The top strategies here involve either using a min heap, which is a data structure that can always give you the smallest node across all k lists very efficiently, or a divide and conquer approach, where you repeatedly merge lists in pairs. Both are great and can get you to that optimal time complexity.
So why is this one merge skill so darn important? Well, it's because it's not just a standalone problem. It's the fundamental engine that drives one of the most efficient sorting algorithms we have, merge sort.
And this is where it all comes together beautifully. Merge sort for linked lists works by first splitting the list in half, again and again, until you just have a bunch of single nodes. And hey, a list with one node is already sorted, right? Then, it uses the exact merge logic we've been practicing to combine those sorted halves back together, piece by piece, into one final, perfectly sorted list. It's brilliant.
Okay, before we wrap up, let's just quickly go over the common pitfalls. Forgetting the dummy node is a big one. It just leads to messy head-handling code. It's also really easy to lose your next pointer when you're relinking everything. Oh, and a huge one is forgetting to attach the leftover part of the longer list at the very end. And finally, like we talked about, returning the dummy node itself instead of dummy.next. Keep an eye out for these.
So, I'll leave you with a final challenge to really test what you've learned. Given these two lists, what does the final merged list look like? Pay really close attention to how you'd handle those duplicate values. Go ahead, pause here, work it out, and see if you've truly mastered the merge.